There's a question from Garvit who asks, what kind of research happens in the ideal world? Which was on a slide that was in the
ideal world, meaning if human species behave exactly rationally and everything.
Yeah, the world we wish for, aspire to, and any kind of ethical inquiry would fall into that world.
Yeah. So if we were ideal people, let's assume that we have the kind of think education that we provide has effect in the next, let's say, 30 or 40 years and so on. So there's a different kind of world, different kind of humans who are all well educated. Then they would be perfectly rational in the way we have defined it. They will not be swayed by emotional considerations in the considerations of truth and so on. And they'll be perfectly ethical. And, a bunch of other considerations. It's an ideal, as Tara talked about, the ideal world, or the kind of world that we aspire to, where everybody has health, everybody is physically fit, everybody is intellectually fit, ethically fit, spiritually fit, economically fit. All these parameters of well-being are satisfied. That is the world that we aspire to.
All right. We have Deesh says also the math world is the ideal world.
That's a different meaning for the ideal world.
Yeah.
It's idealized world. So when I think Arvid's question was about ideal in the sense of the world that we aspire to. Whereas the mathematician's world is not the world that mathematicians aspire to. It's the world that they imagine and construct. So, of course, Plato thought about it as ideal world, as a world that already exists above us. But that is not the way we think about it. Most of us don't think about it that way. The transcendental world. That transcendental world is not necessarily the world that we aspire to. A transcendental world is a world in which you have perfect circles and lines whose width is zero. That doesn't exist in this world because we will not be able to see those lines. So there's that mathematical world is different from the world that we aspire to.
Right. Siddharth has raised his hand. So please, Siddharth.
Siddharth, can you come on video? Yeah. You have to unmute yourself.
You're not able to?
Oh, okay.
Let me try again. How about now?
Siddharth is still unmuted. Sorry, Siddharth is muted.
Yeah.
It worked. Just on Garvit's question, is my understanding right that what Mo described is Mo's ideal world? And I feel like a topic of research is understanding what are the different ideal worlds that people have. So,
yes.
Right. So that's a potential research topic in the ideal world space.
Yeah.
And how is that shaped by the real world that we're in?
The assumption that we are making is if you take the opposite case, for example, we said in the world that we aspire to, everybody is healthy and physically fit. Suppose you negate it. In the ideal world that I aspire to, everybody is unhealthy. I don't think anybody would say that, right? If I say in the ideal world that I aspire to, there is no crime, there is no violence, there is no hatred. Even the people who are actually violent will not say, no, we do not subscribe to that. We want a world with violence. Who will say that? Even a serial rapist will not dare to say, we want a world with violence. So they will pretend to subscribe to what we.
No, I think Siddharth is right in that if you look at it as a world in which we can do research, a world about which, a domain about which we can do research, then that is different people are going to aspire to different aspects of that.
Okay.
And each of those you would be able to. So you might want to take some kind of looking for universal ethical principles, maybe, but whatever. I mean, there's a whole range of things that you can do within that, but that's the general domain.
Yeah.
That's all it is. Yes.
So, Siddharth, what you mean is that within that broad umbrella of the ideal world of well-being that we aspire to, each of us would go for some particular aspect. So if I were to do research, I will go for the intellectual health. Somebody else may go for the ethical health, and yet others for economic health. Yeah, those are different paths that we choose for those final goals.
All right. We have spent a significant amount of time on the question of ideal world. So, yeah, Pankaj has a question. Pankaj, please unmute yourself. Pankaj, are you able to unmute or not able to unmute?
I don't know.
Okay. How about now? Should you try now?
Point,
yes, now it's good. Thank you, Aditi. Thanks, Sarah and Mo. Really. So I was wondering, it depends on what kind of research you are doing, right? Because in my sense, when I want to learn about the world, then I need to follow the structured way of logic and reasoning to understand the truth about it, right? To make sense out of it, and to help myself to understand about the work, I need to have some hypothesis, and it leads me through the evidence of the world to discover the truth. What we have infers as a human being, but what comes out with the empirical evidence, which is different. So dreaming is what I was trying to understand. Dreaming, maybe what we would love to have in the world, but research help us to understand the reality first to achieve that world which we have dreamed about. Right.
Yeah.
So I also wanted to understand more about classical reasoning and non-classical logical structure. Actually, I didn't get clarity on that. If it will be great if you can also make a light on it.
In classical logic, if you arrive at a conclusion, that conclusion can never turn out to be wrong. That's one thing. Okay. If the reasoning is valid and the premises are true, in classical logic, the conclusion can never be wrong. But that is not how it is in science. The reasoning could be valid, and we may take the premises as credible, and yet we might discover evidence against it. Also, probabilistic reasoning, which is less than total certainty, is not allowed in classical logic. Classical logic is binary in the sense its truth values are only true versus false. It doesn't allow in between, let's say a third value, true, false, neither. That is not allowed in classical logic. But in the logical system developed in the 19th century, the first non-classical logic was three-valued logic, even for mathematics. They proposed this. It didn't, of course. It didn't stick in mathematics. Then classical logic doesn't say anything about causation. So if you want to develop a causal logic, it has to be outside of the narrow circle of classical logic. So these are the different ways in which we need to deviate from classical logic in order to do reasoning. So causal reasoning is central to biology. And you cannot do the kind of reasoning that biology needs using first order logic. You need to do something else.
Tara, were you saying something?
No, I was saying that at some point Chitra had unmuted herself and was asking a question, but now she's put it in the chat box, so
I see.
We'll pick it up there.
Yeah, sure.
Okay.
I think I'm sorry, Pankaj, I know you want to unmute yourself again, but we have a bunch of questions related to correlation and causation, which we haven't taken yet. So perhaps for a couple of minutes, we could switch to questions that we got from the live stream and take those. Vignesh asks, could you elaborate a little more on implicational relation and the assertional causal relation? For instance, take if an organism has an eye, then it sees, versus eye causes seeing. What is the difference between implicational and assertional causal relation here?
The first thing to understand is that the correlational classical logic is about the relation between propositions. You have to say, if such and such propositions are true, such and such other propositions are true. Now, notice you are talking about the world of propositions. And of course, you have to translate the world of propositions to the world that you are interested in, the world of ethics or the world of the existing world that science is interested in, and so on. Causality, on the other hand, is about the world that we live in, events in this world. So if in this world fire exists, then that fire will cause smoke, is what causal reasoning is telling you. So it's a relation between, cause-effect relation is between events in the world. It is not about propositions. But we have to somehow or other convert statements about the world of events, causal relations in the world, to propositions. In order to make that into logic, we have to say, if you are saying something about fire causing causing smoke, so you have now moved from the world to the proposition, and then you assign truth values. That is how logic works. But there is still a fundamental difference between the two. So, which is one of the reasons why causal logic has not become formalized. In fact, the attention to causal logic is only about 20 years old. People have discovered that causal logic is necessary for a large number of things. You need this in artificial intelligence. You need it in learning, computer learning. You need it in data science. You need it in infectious study of infectious diseases. For example, COVID is a classic example. If you want to construct a theory of COVID, how the virus causes illnesses, obviously you need causal logic. If you want to study cancer, you need causal logic. Medicine cannot be done without causal logic.
Right. Tara, anything to add?
No, I was just thinking if there are clusters of questions, similar questions, if we could put them together.
Yeah. We've been trying to do that. So actually related to what you just said, Garvit had said, can we say that causal relations give more information than correlational statements? Also, if we have causal statements, why would we need correlational statements?
Because there are certain kinds of questions which are not about causation. For example, if I want to construct a theory of structure in biology, anatomical structure, we are simply saying that there is a correlation between, let us say, the existence of beak and the existence of feather. There is a correlation. You are not saying that beak causes feather. We are just stating correlation. Mathematical reasoning doesn't say anything about causation. It is talking about truth of propositions. That's it. So you need both.
Yeah, it just so happens that whenever you have a causal relation, there is also a correlation. So causal relations are a subset of correlations. Yeah. So sometimes it's a little misleading. You need to factor out the different aspects of it and figure out which one it is. Right.
To give an example, if you want to talk about the relation between circumference and diameter of a circle, you're not going to say circumference causes diameter, diameter causes circumference. That doesn't make any sense. That is clearly correlational.
Right. I just want to tell everyone, if you'd like to ask a question, please use the raise hand feature. You can find it on the, where can you find it? Yeah, all right. Tarun has found it, and maybe someone can put it in the chat if they haven't, how they found the raise hand question. Tarun, yeah, please unmute yourself and ask your question.
Yeah, thanks for that. So my question is like, so do all the formulas, whatever we have, are these correlational logic, or there can be formulas which has causal logic?
Formula in mathematics and physics, yes, they are all correlational formulas. That's right.
Okay.
There is no causation in the equations in mathematics and physics, or in all the equations that we have been using so far. They're all correlational, which is one of the reasons why Russell said that causation has no place in scientific theory. What you were saying was that scientific theories that use equations, for him, physics is a classic example. There is no causation in any of those equations. So he said causation is an illusion. It should not be part of science. It is not part of science. Newton, when he formulated the theory of gravity and motion, was talking about correlations, not about how gravity causes motion or causes, Newton's case, gravity causes acceleration. But that is not the case anymore. Now, even Russell changed his mind later and he said, okay, we can bring in causation provided we understand what it is and we have a theory of causation, a formal theory of causation. In Russell's time, that did not exist. Now, even physics is beginning to look for causal theories. So there is a causal network theory. People are trying to build in causation into space-time. But that work has only just started. It'll take time.
Aren't chemical reactions causal relationships?
Chemical processes are causal, but equations say nothing about causation. The equations where you balance say something like the number of atoms on the left-hand side and the number of atoms on the right-hand side are the same. And then it also says that given the molecules on the left, you can infer the molecules on the right. There is no causality, there is no causal reasoning in any of those equations. It's in the nature of equations. So we could, of course, use the arrow notation in chemistry to develop a causal formalism. But that part has not been done properly.
All right. Garvit raises in the chat that the first part of his question was not answered. In that, do causal relations provide us with more information than correlational statements?
I'm not sure what it means to say more information. It's a different kind of information. Yeah. It's actually it's not about information, but about how we deal with information. We deal with information differently in causal reasoning and correlational reasoning. And we arrive at different kinds of conclusions, that's all. It is not about the data, but about what we do with that data.
Right. We've had a couple of questions on defeasibility in the from the live stream, and a couple of questions on inductive and abductive reasoning also from the live stream. Perhaps we can take those now. So one question is, can't we convert defeasible logic into classical logic by adding some operations like and or, those being the operations? And there's another question which says, can you please elaborate what we mean when we say defeasible? So perhaps.
Let me begin with the second question. When we say defeasible, what we mean is, given one set of premises, we conclude conclusion one. Given another set of premises, we conclude not that conclusion. So we have a logical contradiction. If you conclude Q under one set of premises, and not Q under another set, if both conclusions are accepted, then we get a logical contradiction. Q and not Q. Defeasible reasoning is a way of solving that problem. Okay, so that when you get a logical contradiction between two sets of premises, we take only one of the parts of the contradiction. If you want to know more about this, another term for it, perhaps a more popular term, is non-monotonic logic. There are some other words for it, but if you do a search on non-monotonic logic, you will get more information on this. So that's what defeatable conclusion from one set of premises can be defeated by conclusion from another set of premises. That's a basic idea. Now the question is, can you do this? Can you stipulate, sort of mimic this in classical logic by adding exception clauses? So, for example, you could say in the example that I gave, you could have an except clause. And this is what legal documents do. They have these, if such and such, then such and such, unless it is such and such, unless, and so on, so on. And they build in all the exception clauses. And all the conflict clauses are built into classical logic. But then for that, you need to have perfect information. You cannot work with uncertainty. Imagine, for example, doing that in medicine. You need to know about all the possible clauses, possible causes in the world. So this is what economics does. Economics assumes perfect information. That is, classically, economics assumes perfect information. But that's not the case. Perfect information does not exist. You have to be a god to do that. So humans to do this, you need defeasible logic. God can do with classical logic.
All right. So we have a bunch of interesting questions. One about inductive and abductive reasoning, like I mentioned before, and a few more about the ideal world discussion that we were having early on. But it's close to 8 o'clock, and so I was wondering that the questions we weren't able to answer now, we will answer in writing perhaps after the session, as we usually do. And if it's okay for us, I wanted to ask the participants if it's okay for us to take those questions about inductive and abductive reasoning now and then close with that. If you're willing to stay on for a few more minutes, we'll be happy to take a couple of more questions from you. Right, Savani, if that's the way to say it, she says she can stay. Okay, Garvit also says she can stay. Chitra also says she can stay.
Okay.
So we'll just take a few more questions and perhaps, all right. If you have any questions, a good time to use the raise hand feature. And
any question that doesn't get answered, we will send a response.
We will send a written response later. All right. So there's a question from Aditi Kulkarni. She says, so some theories have inductive reasoning which can have exceptions, right? And there's another question from Garvit. I didn't understand the difference between inductive and abductive logic. Could you please explain?
Okay, with the induction versus exception. Okay, the difficulty with the notion of exception is that if your observational generalization makes a false prediction, then you can always say, oh, that's an exception. Every time somebody comes up with a counterexample, you can say that's an exception. That's unhygienic habit. So rather than saying exception, state that in your observation generalization. All right. So for example, if you say something like there are no mammals with wings, and somebody says, hey, how about bats? Oh, that's an exception. Okay. Now that habit of functioning is a really unhygienic, bad habit. So what you should do is to look for counterexamples. So instead of saying exception, use the word counterexample. Counterexample is an example that shows that you're wrong. Do not pretend that you're right and dismiss everything as exception, but accept counter evidence. That's a different way of functioning. So instead of using the word exception, say counterexample. Acknowledge that you're wrong.
Can I just add something? Why this discomfort with exceptions? See, the moment you allow exceptionality into your statements, you can have a whole laundry list of exceptions. And then it could get to a point where you're not making a generalization at all. And it is to avoid that you avoid exceptions as much as possible and build it into your generalization. Right?
So here is an example. If you want to say something about the past tense in English, usually the most general rule is you form past tense of English verbs by attaching ed. So walk, walked. So you say English, you can get past tense in English by attaching ed. Then somebody would say, what about the verb cut? You don't say it's an exception, and then you add that to the rule. Past tense in ed is created by attaching ed except for cut, and you list all the verbs. Finite number of exceptions, you list the finite ones. But defeasible logic allows you to do something else. What you do is, for such and such verbs, use this rule, and that defeats the other rules. Those are technical ways of dealing with it. We won't go into that here. But anyway, unless the exceptions are listed and explicitly put into the rule, you don't dismiss things as exceptions. You have to say, those are counterexamples.
Right. Pankaj has raised his hand. Do you want to unmute yourself?
So I don't have a question per se, but I just wanted to understand in the which kind of logical reasoning we do in a philosophical inquiry compared to the scientific discovery to understand the material world.
In philosophical inquiry, you use all these modes: the classical logic, defeasible logic, abduction, all of them. There is no distinction between the modes of reasoning in philosophy and the modes of reasoning in science.
But in the different topic, we use a different kind tool of the logic, right? As you mentioned, in the Nyaya Darshan, they use a different kind of tool, and in the Buddhist inquiry, there is a different kind of tool they use to understand moksha. Let's say death itself. But in the materialistic scientific world, it's a different approach. So, but I couldn't figure out which tool they use to explore these realities.
Yeah, let's take as an example ethical inquiry. And ethical inquiry, given us ethical theory, we need to deduce whether a given action is ethical or not. Okay, that's a matter of prediction of a certain kind. So if you accept such and such ethical axioms and definitions, what judgment should we make about such and such action? So, for example, should killing butterflies be considered as unethical? You can deduce that from an ethical theory. For that, you use non-classical deduction. It can be probabilistic or defeasible. Typical ethics requires actually defeasible deduction. However, how do you justify?
Which can be unproven in the future.
Pardon me?
Which can be unproven in the future, can be changed.
Yes,
or subject to
given the circumstances. So, for example,
it is subject.
Suppose you are told that somebody's told something. Is that bad? In defeasible reasoning, the first conclusion will be yes, it is unethical, and then you give the context in which the stealing took place. And when the context took place, we'll say, oh, I withdraw that conclusion. The conclusion ought to be that was ethical. And then you look at more context, you change. So this is your conclusions keep changing from yes to no and no to yes in defeasible logic. But this is still defeasible deduction. If you want to justify an ethical theory, rather than using an ethical theory to arrive at ethical judgments, if you want to justify the theory itself, then you use abductive reasoning. We haven't, we'll need a separate course on ethics to deal with how you do that.
Yeah. To go back to the earlier question, which was about the difference between inductive and abductive logic. I'm not sure if we addressed that, which is why I'm bringing it up again. How can we? What are the fundamental differences between inductive and abductive logic?
Okay. Let's think of this as induction would be given a set of data points or given a set of observational reports. What observational generalization can we make from the sample to the population? That's what induction in this sense means. Abduction, on the other hand, can do something else. Given a theory and one data point, how do you interpret that data point? Okay. So take, for example, the doctor's abductive reasoning. The doctor is dealing with one patient. And let's say, just say one symptom. And the doctor has to arrive at a conclusion about the illness. That would be abduction. This is not induction because the doctor is not taking a sample of data points and arriving at observation generalization. The doctor is interpreting a particular patient's symptoms. That will be abduction. So let's take another example.
Sorry, can I add something there? The doctor is taking one patient's symptom and interpreting it within a given theory that the doctor has.
Yeah.
That's not the case in induction.
Yeah.
Sorry, yeah, I interrupted.
Maybe I should give this example. You are looking at the sun, and let's say at 7 o'clock, and you're looking at the sun again at 8 o'clock with maybe dark glasses, and you discover that the sun's position is different from the earlier position against the horizon. The sun is now farther away from the horizon. Okay, that is your observation, that the sun is at a greater distance, from the horizon of the earth. There are two ways of interpreting it. You could say, the sun is revolving around the earth. That will be abduction. Abduction within the geocentric theory. You could also say the earth is rotating. That's also abduction. But two different abductions, you get two different theories, you get conclusions, different conclusions. This is abduction. That is not what I've just described is not induction. I hope that makes it clear.
Yeah. There's a question from Chitra. She says, can we say inductive reasoning and deductive reasoning are opposites of each other?
Sorry, what was that again?
Can we say that inductive reasoning and deductive reasoning are opposites of each other?
Opposites.
Opposite is too strong a word.
Yeah.
It's a different. So biology and mathematics are not opposite. They serve different functions. Right?
All right. Tarun has raised his hand, and perhaps as has Garvit. Perhaps these will be the last two questions we take today, and we will end with that. Tarun, please.
Yeah. Thanks for the difference between the induction and abduction. Induction is very clear now, but then how abduction is different than the deduction from the example you gave?
Sorry, how abduction is different from?
Deduction logic.
Deductive
logic.
I see. Okay. Yeah.
One way of answering that question would be say deduction is when you have a theory and you want to arrive at a prediction from the theory, you use deduction. Predictions are derived through deduction in a scientific theory, let's say. Abduction, on the other hand, is you have a particular data point and there is a theory and you want to interpret the data point within the theory. That is abduction. There is another kind of abduction. You have a set of observational generalizations and you want to explain them and you want to arrive at a theory and justify a theory. That'll be a different kind of abduction. Anyway, abduction means the movement is different. Abduction moves from the observation to the theoretical interpretation or theory, whereas deduction moves from theory to prediction in two different directions. But induction is also the same type. Induction is also the move from data points towards observation generalization. But induction doesn't take care of theory. Abduction does.
Thank you.
Yeah. I think we'll take Garvit's question now. And I'm sorry, Prasad. I'm not sure if we have the time for your question, but we'll try.
Okay, so Professor Mohanan, you said that.
Sorry, if you call me Professor Mohanan, I will not answer. No prefixes.
Yeah.
Okay, Mo. Yeah. Professor Mo, right?
No, Professor.
Okay. Yeah. Okay, Mo. So you said that using a lot of exceptions is unhealthy and unhygienic. So will we call the subject of chemistry as unhealthy and unhygienic? It has a lot of exceptions, right?
As is actually practiced. So what I'm suggesting is in a rigorous academic work, we should not do that. So take something like the anomalous expansion of water. If you say something like everything expands when heated, clearly there is a counterexample. water at 4 degrees centigrade. Okay, it expands when heated, but it also expands when cooled in both directions. So when you say something like everything contracts when cooled, is not true about water at 4 degrees centigrade. Rather than saying it's an exception, what you should say is that it's a counterexample to our statement. Then the next step will be, why is it a counterexample? Why doesn't it work there? What are the reasons? When you construct a theory of the anomalous expansion of water, then there are no exceptions. The combination of the general theory and the particular theory will do it. Okay, let me give you another example. I take a piece of iron, and then I say I'm going to drop it, and your prediction will be it'll come down in a straight line. And I say, okay, let us test this theory. I drop this, but instead of it going down, it just goes up. What would you say? Would you say, oh, that's an exception, that's okay? No. As a responsible researcher, you want to find out this tells you your prediction is wrong, and you have to find out why the prediction is wrong, and look around and say, there is a strong magnet on the ceiling, and the piece of iron is moving towards the magnet. So what happens here is the combination of the theory of gravitation and the theory of magnetism will give you the right prediction. Another example, the theory, Newton's theory or Galileo's theory predicts that a dry leaf, when you drop from, let's say, 6 feet above, will come down exactly in a straight line. That is not what it does. It moves around in some, crazy way. It comes down, but not in a straight line. Should you say, oh, that's an exception, and stop there? No. You got to find out why it behaves differently, why the prediction is wrong. That is where you need air resistance theory.
Can I just say something then? See, when you're talking about exceptions, you're talking about exceptions to a pattern, right? And what we need to realize is that when you have a pattern in a particular domain, you might have sub-patterns within that. So the example of the past tense in English came up earlier. So you have different kinds of past tenses. Walk, walked, and then you have sing, sang, bring, brought, and so on, go, went, etc. Now, what do you do with that? Do you still want to give up the general statement that the past tense is ed? No, because there are many reasons why you want to keep that general pattern. Because, for example, when children are learning the language and they make mistakes, when they don't know the past tense of something, they say ed. And also, if you look at the verbs in English, you find that most of them go with ed. And for many reasons, that there is a general pattern there. What we need to say is not that these are exceptions, but there are sub-patterns which have their own status. And this is where one way of using defeasible reasoning comes in. You say, you give all of the special cases first, you state your special patterns first, and with whatever is left over, that's where you have your general pattern. That's one way of doing it. And that's probably what happens in a lot of chemistry.
There are also cases where there is what you might call law interaction. When you have different laws, they interact. The interaction gives you a different kind of prediction. So you don't, in science, you don't just take into account gravity. You take gravity, electricity, and magnetism. All these laws have some effect on motion, and you put together all of them. That is also true about medicine. So interaction between laws is given by a different system of logic. That is where defeasibility comes in.
All right, we're a full 17 minutes after 8. So since Prasad's hand is raised, we can just end with this. Prasad?
Sorry, it's just a small question. If I know that fire causes smoke, then I can say that smoke. If I see a smoke, there is fire, right? So is it like double implication causal relationship?
So reasoning from the effect of the cause is abduction. It's not double implication. But in the case of, if you infer fire from smoke, you should also consider other possible causes. Maybe the smoke was caused by something else. So you have to look for alternative causes. I don't know if my answer addressed your question.
Oh, yeah, it did.
Okay.
It did.
It is not double implication in the sense if P then Q and if Q then P. No.
Yeah.
The two directions have very different flavors.
All right. We've had a bunch of interesting questions on counter examples as well in the chat, which we will have to take up in writing later on. We've noted these questions down, and thank you so much for asking these questions. If you think this kind of a Zoom session was useful, we could try again next time. And if you find this more productive than the live session.
And sorry to all those who we couldn't take your questions.
Yeah, sorry.
Yes.
We will answer them.
Yes, we will definitely take up by writing. Thank you for joining us, and we hope to see you next week for the next session.
Yeah. Bye.
Okay. Take care. Good night.
Good night. Bye-bye.